Hello all, this is Scott Moore, one of the Senior Technical Account Managers supporting HPE at Ingram Micro. And in this session, we're going to be going over some networking basics. So the agenda for this session, I'm going to go over some basic network types and speeds. We'll talk about the basic network layout, look at the components that make up a network, the NICs, the cables, and the switches. And we'll talk about some other components, things like routers, firewalls, and access points, and put them all together. So in reference to common network types and standards, the current common Ethernet standards are 1 gig, 10 gig, and 25 gigabit per second. 40 gig, 50 gig, and 100 gig Ethernet and InfiniBand technologies are intended for creating high-speed network backbones between servers and switches, and you don't see those in much use on the client side, on the desktops and notebooks yet. And they're not in extremely wide use at this point. Then you also have wireless, 802.11 something. Wireless is generally not used in servers due to its limited speed and due to security issues. The nice physical security aspect of Ethernet and InfiniBand is you can't get access to the network unless you physically have a cable plugged in. That's not necessarily true for wireless. Wireless is easy to get access to, since we're only talking about all you need is a radio receiver and a radio transmitter to get onto the network. So between the security issue and the speed issue, not a lot of wireless built directly into servers in the data center. So here's a table that kind of gives you a breakdown of a lot of the different standards between Ethernet, wireless, and InfiniBand. What's notated in red is pretty much where the sweet spots are right now for the networking. So like I said, the Ethernet world, 10 gig and 25 gig, probably the most popular nowadays. Wireless, you can see the speeds are significantly less than they are for cabled Ethernet. And InfiniBand, the reason it's used as a high-speed backbone between different networking, or between different servers in a cluster or a high-performance computing environment, is because the speeds exceed what's commonly available in Ethernet. Now, there are other types of networking besides what's listed here. Intel OmniPath, for example, Cray Slingshot, but those are really kind of niche technologies. You see them sometimes in the high performance compute or the server backbone world, and that's about it. So our basic wired network layout, this is basically the same for Ethernet or InfiniBand. Of course, the components are all going to be different, but the layout is generally the same. Every device that connects to the network must have a network interface card, or a NIC. This can be an add-in device like an expansion card, a PCIe card, or it could even be built in like it is for a lot of servers, printers, and NAS devices. Here, I'm showing a single NIC port coming off of each network interface card on each of the two servers and going to a switch. This is common for clients such as desktops or notebooks, but it's more common, I would say, for servers to have multiple NICs and multiple cables going out to the switches. Basically, in a wired networking layout, you have every device that you want to be able to talk to one another on the network having one end of the cable plugged into a NIC, and you have the other end of all the cables plugged into a device called a switch, and everybody who connects to the switch can talk to everybody else on the switch. Now, there are some reasons that we would have multiple network interface cards inside a server or inside a data center device. Some of those reasons include redundant NICs allow for faster failover of a bad cable, bad switch, bad port, or a bad connection. There's something called trunking or aggregation, which allows multiple NICs to add their bandwidth together for better throughput. Not so much something you would do on a desktop or a notebook side, but on the server side, where you're going to have multiple devices all competing for the attention of the server. Adding more throughput to the server is a good thing and will help your performance. NAS storage is storage that's directly connected to a network. So if you have a NAS device, you're going to want multiple ports in that. Also, iSCSI storage area networks, or SANs, allow servers to connect to storage over an Ethernet network. Another reason you're going to have more Ethernet on your network. And finally, virtualization Best practices usually have separate network interface card ports for each virtual machine that you're going to run on the same physical server. When it comes to Ethernet cabling, there's a couple different types. First, we'll talk about copper cabling. Copper cabling comes in different categories: category 5, 5E, 6, 6A, 7. Each category of Ethernet cabling has 8 copper wires within it, with progressively more twists in the pairs of wires to reduce interference. So a category 7 cable has more twists per foot than a category 5 cable. The higher the category, the faster the supported speed. So I can do gigabit Ethernet on Cat 5e. If I want to do 10 gig, probably going to be safer with Cat 6a. The more twists in the cable, the less interference. The more interference you have, the slower speed you're going to be able to push through the cable. Now, these cables are backwards compatible. So for example, I could use Cat 6a to run a slower speed network, like a 1 gig Ethernet network. And there's another type of copper cable called a DAC, or direct attach copper. SFP plus direct attach DAC cables are used for 10 gig. And the idea there is SFP connections usually require fiberglass or fiber optic connections, but they can be quite expensive. So rather than get an SFP plus at each end of your cable and a piece of fiberglass in the middle, you can get a DAC cable, which is a copper cable that has a connector at either end that would fit into an SFP port on a switch or a NIC that regularly uses fiberglass. So this is getting to some of the technical stuff that I want to make sure you can look at it and say, oh, okay, I get it, it makes sense. Then you can go ahead and promptly forget why it makes sense. There's more important things to life to memorize, like, your address and your wife's name and things like that. Fiberglass cabling. Two main types of fiberglass cabling. We have what's called multi-mode. Multi-mode is used for short distances. And by short distances, when I'm talking about fiberglass and optical signals, we're talking about up to 400 meters, so a little over 1,000 feet. Also referred to as shortwave, short haul, or short reach. And there are multiple paths for light to travel down a multi-mode cable. And that's exactly what multi-mode means. Mode is a path for a beam of light. So if it's multi-mode, it supports multiple paths for a beam of light. As you can see from the diagram on the bottom there, the idea is you shoot a light pulse down or multiple light pulses down. They bounce around the inside of the fiberglass until they come out the other end. Over short distances, again, we're talking relatively short distances, 1,300 feet or less, the order in which you send light pulses down one end of the cable will be the same order that they come out the opposite end of the cable. If you go beyond that 1,312-foot limit, that's not always the case. So we have single mode cables. Single mode cables, also known as long wave or long haul or long reach, have a single path for light to travel. So there's not a lot of room for it to bounce around. So at this point, it's forced that any light pulses that are put into the cable come out the far end of the cable in the same order. Those single mode cables are good for distances of up to 6 miles or so long. So if you've ever seen construction work being done on the thruway and you see these huge spools of cable alongside the thruway, what they're probably doing as part of that construction is putting down single mode cable for fiber optic connections between multiple sites, perhaps rest stops along the thruway. In addition to these two types of cabling, there's things that we refer to as transceivers. SFP transceivers, or small form factor pluggable transceivers, convert between light signals and electrical signals for speeds up to around 28 gigabit per second. There's also something called QSFP, or quad SFP, and it supports 4 simultaneous lanes of SFP speeds through the same connector, so up to 112 gigabit per second. Usually switches and some high-end NIC cards have SFP or QSFP connections on them. You get a QSFP or SFP transceiver, install it into the card or into the switch port, and then you connect to the other end of the transceivers via a piece of fiber optic cable. Switches. Switches connect clients and devices to a network. There are what they call unmanaged switches, and there are things called managed switches. With an unmanaged switch, everybody talks to everyone else. So anything that's plugged into the switch can talk to any other device plugged into the switch. If you're running a network at home, this is perfectly fine. You want anybody's notebook who's plugged in to be able to talk to the printer that's on the same network. Managed switches, however, offer some differences. You can do things like VLANs, or virtual local area networks. So I can set up which ports on a switch, on a managed switch, can talk to each other and which ones can't talk to other ports. And in that way, I can have everyone connected to a single switch. By setting up VLANs, I can make it look like they're all on independent switches. So certain people can talk to others and certain people can't. If you're setting up multiple work groups or different departments within a workplace, you might want to use VLANs to segregate your traffic. There's a feature called quality of service available on some switches. Quality of service guarantees bandwidth to certain network ports in the event of a slowdown or any sort of traffic problems on the network. So why is that important? Think of things like IP telephones or streaming video. If you have bandwidth problems on your network and everyone is adversely affected and everybody slows down, you're going to drop packets in your video, you're going to drop connections on your IP phones. With quality of service, you can make sure that anytime there's performance problems on a network, your phones continue to get as much bandwidth as they need, and your video streams continue to play uninterrupted by assigning them higher rankings of quality of service. There's also something called power over Ethernet, which we'll talk about a little bit more in a second. But power over Ethernet, or I should say power over Ethernet switches, are devices that can actually power network connected devices through their data cable. So you don't need to plug these devices into power as well. If it's a power over Ethernet device, you can plug it into a power over Ethernet switch, and power is provided to the device right through the cable. Some common examples of power over Ethernet devices, things like access points or security cameras. As I mentioned before, it's for connecting network devices in inconvenient places or things that might be far from power outlets. In the case of an access point, in an auditorium or gymnasium, I might want an access point high on the wall to get better coverage over a large area. Unfortunately, my power outlets are where? Usually 2 feet off the floor. So I don't want a power cable that I have to plug in 2 feet from the floor, stretching up to something that's 25 feet overhead. If I can just run a regular Ethernet cable, maybe through a drop ceiling, and plug it into my access point for data, I can deliver power through that same cable, DC power through that same cable. Security cameras, the same thing. If I have to plug in every security camera into a regular wall outlet, it'd be pretty easy to overcome that physical security simply by unplugging the camera. If I have things like a drop ceiling, where again, I can run Ethernet cable through above the ceiling or through channels above the ceiling or under the floor even, I can plug directly into the cameras, get my data and my power through a single cable. And all those devices are powered by the switch. The power over Ethernet switch is the only device that's actually plugged into traditional power outlets. So as I mentioned, power and data delivered over the same copper network cable. And in addition to wireless access points that we mentioned, security cameras, thin clients, especially in education, for example, are another example of devices that might be used that could be powered over Ethernet. Routers, also known as gateways, are devices that connect dissimilar networks together. by routing signals between them. We talked about switches and how when you connect something to a switch, everybody can talk to one another. Well, switches are for a specific type of networking. So I would buy an Ethernet switch, or I would buy an InfiniBand switch. What if I have two dissimilar types of network that need to talk to one another? That's when I would get a router or a gateway. If you think about it, if you have internet access at home, you might have a router in your house. You have some sort of cable that's connected to the internet coming into your house from outside. Who knows what sort of network is on the other end of that? Doesn't matter. Once it comes into your house, it usually provides Ethernet ports that you can plug directly into. It also usually has a wireless antenna, so you can connect wirelessly to it. So you're connecting both external internet, Ethernet cabled, and wireless all through a single device. So the router or gateway essentially functions like a switch, but allows dissimilar network devices to talk to one another. Another kind of specialized networking device is a firewall. Firewall is a security device. It sits between your internal and your external networks. So the same place in your home environment, the same place your router would sit, and it blocks unsafe packets from reaching the other side. Typically, you're using it to block unsafe packets from out on the internet, coming into your production network, or coming into your home network. When we were talking about power over Ethernet, I mentioned wireless access points as well. Wireless access points are for connecting network devices wirelessly via radio signals. They connect back to a network switch via a regular Ethernet cable. So even though they are wireless access points, they are cabled devices because they need to connect back via cable to an existing network somewhere. They're frequently powered over Ethernet, although that's not always true. And they convert the signals between wired and wireless. So you can kind of think of it a little bit like a gateway. It does have an Ethernet connection cable going back to a switch somewhere, but it does have radios in it to provide wireless coverage to any clients in the area. And that brings us to the end of our networking basics. I hope that was useful or a good refresher for some of you. Thanks for your time today.